Download this code from codegive.com, link in the description below. OK, let's dive into the world of accumulators, with a special focus on context preservation. We'll break down the concept, explain why it's useful, explore various accumulator implementations, and provide code examples in Python. This is part 1, so we'll cover the basics and some simpler accumulator patterns. We'll build towards more complex, context-aware scenarios in subsequent parts. What is an accumulator? At its core, an accumulator is a variable or data structure that progressively collects and aggregates values over time or across iterations. It's a fundamental concept in programming, especially in scenarios where you need to perform a calculation or gather information incrementally. Think of it as a running total, a string builder, or a list that's constantly being appended to. Why use accumulators? Accumulators are useful in the following common scenarios. 1. Calculating sums, products, averages *, the most basic use case. You start with an initial value, example 0 for summing, 1 for multiplying, and add / multiply each subsequent value to it. 2. Building strings *, concatenating strings together in a loop or function to form a larger, more complex string. 3. Collecting data into lists or sets *, appending or adding elements to a list or set as you process data. 4. Performing reductions *, accumulators are essential for performing reduction operations, where you reduce a collection of data, like a list, to a single value. 5. State management *, accumulators can be used to maintain state across multiple function calls or iterations, allowing you to build up a result based on a series of operations. Context preservation, the key difference. Context preservation is the crucial element we'll focus on. In many accumulator scenarios, it's important to maintain additional information or state alongside the accumulated value. This context allows you to make more informed decisions about how to update the accumulator. Track the history of the accumulation. Pass intermediate results to other parts of your program. Handle edge cases and exceptions more effectively. Simple accumulator examples, without context preservation. Let's start with the basic accumulators, where we're not explicitly preserving extra context. In these examples, the accumulator itself, the accumulator variable, holds only the result of the aggregation. We don't keep track of any other information about the process. Accumulators with basic context preservation. Now, let's introduce some context preservation. We'll start with simple examples to illustrate the idea. Example 4, summing with error tracking. Suppose we want to sum a list of numbers, but we also want to track how many invalid, non-numeric, values we encountered. We can use a tuple as our accumulator to hold both the sum and the error count. In this case, our accumulator is a tuple, sum, error_count. We're preserving the number of errors alongside the sum. This allows us to understand the quality of the data being processed. Example 5, building a string with length tracking. Let's say we're building a string, but we also want to keep track of the length of the accumulated string. Here, the accumulator is a tuple, string, length. We keep track of both the accumulated string and its current length. Example 6, collecting even numbers with index tracking. We might want to collect even numbers and also store the indices where they were found in the original list. Now, our accumulator is a tuple containing two lists, one for the even numbers and one for their corresponding indices. Using named tuples or dictionaries for context preservation. Tuples work, but they can become less readable as the number of elements in the accumulator grows. Name tuples and dictionaries provide better clarity. Using name tuples or dictionaries makes the code more self-documenting. You can clearly see what each element of the accumulator represents. Note that name tuples are immutable, so we need to use _replace to create a new name tuple with the updated values. Dictionaries are mutable, so you can update them directly. Key takeaways from Part 1. Asterisk accumulators are variables that progressively collect and aggregate data. Asterisk context preservation involves maintaining additional information, state, alongside the accumulated value. Asterisk tuples, name tuples, and dictionaries can be used to implement context-preserving accumulators. Asterisk name tuples and dictionaries generally lead to more readable and maintainable code. Next steps, for Part 2. In the next part, we'll explore more advanced accumulator patterns and real-world use cases, including asterisk using classes to encapsulate accumulator logic and state. Asterisk accumulators for parsing and data transformation. Asterisk accumulators in concurrent programming. Asterisk accumulators with more complex decision-making based on context. Asterisk using the functools.reduce function for accumulators, and its limitations with context preservation. This tutorial provides a solid foundation for understanding accumulators and the importance of context preservation. Practice these examples and think about how you can apply the concept in your own projects. Let me know if you have any questions.